So far, we've talked about what we would call intramolecular forces, the forces inside molecules. But now we're ready to talk about intermolecular forces, forces between molecules. And we call these IMFs, and I'll often abbreviate it as such. So the first one I want to talk about are called the van der Waals forces. These are non-covalent interactions between molecules. And then there's the essentially a permanent dipole that are from one molecule interacting with another permanent dipole in another molecule. So we often call these dipole interactions or permanent dipole interactions. And again, this has to do with partial charges, right? So we just talked about in the previous video this idea of delta positive and the delta negative. So we're going to have those two things interacting with each other. So for example, acetone, as we drew that for the line angle structure a little bit ago, acetone has a dipole for sure. We've got the oxygen double bonded to carbon and lone pairs, just to be sure. Just like water, acetone also is polar. The oxygen is pulling electrons toward it. So this end of the molecule definitely has a delta minus partial charge. And then the carbon that's double bonded to that oxygen has a delta positive. I'm going to kind of draw it off to the side a little bit there. So acetone's a polar molecule. You could draw a dipole vector like we were previously like that if we wanted to. But the point here is let's see how that acetone interacts with another molecule of acetone. So I'm going to draw another one kind of right below it, just like that. Include the lone pairs. And just like the one above it, this has a dipole, partial negative here, and then partial positive where that carbon is. And the dipole-dipole interaction is actually where the lone pair, the partial negative charge on this oxygen interacts with this kind of partial positive carbon right there. And we can depict that using, say, dashed lines. So the dipole-dipole interaction would look something like that, with those dashed lines right there. And so there's a little bit of an attraction there. There's slightly positive, slightly negative, so there's a slight attraction there, partial attraction in this intermolecular force. We often refer to this one, in general, these dipole interactions, as cling. It's a term I like to use. It kind of reminds you of like static cling. Things are kind of interacting with each other, but you can pull them apart pretty easily. This isn't permanent. These interactions, the dipoles are permanent, but the interactions might not be. So that's a dipole-dipole interaction. Partial charges, opposite partial charges are attracting. And here I've shown it with just pure acetone, but you could see this with a mixture of acetone and water or other things like that. So we'll see other examples of that as we move on. Next up is the hydrogen bond. The hydrogen bond is a dipole-dipole interaction. It's just a very strong one, a special type of one. And this occurs when a hydrogen bond is covalently bonded to one electronegative atom. Okay, so you have a hydrogen that's covalently attached to an electronegative atom, and we're thinking here things like oxygen, nitrogen, and fluorine. For us, oxygen and nitrogen are the most important ones. And that hydrogen will interact with another electronegative atom's lone pair, and that's, again, a non-covalent interaction. So one thing I want to point out is that hydrogen bonds are depicted with dashed or dotted lines only, never solid lines or arrows, and we'll see why when we get into other aspects of this course, why we need to make that distinction. So again, that's a wordy definition. Let's show it in pictures. So I'm going to first draw out a molecule of water and show how it can hydrogen bond with another molecule of water. So we got our H2O, got our lone pairs, and I think we now know that this end of the molecule is partial negative here. And I'm going to draw another water molecule nearby. And I've drawn this strategically because now this end of this molecule is partial positive. And so we now have a situation where we can have a hydrogen bond. we have, look at the definition, a hydrogen that is covalently bonded to an electronegative atom like oxygen, and then it can interact with the lone pair of another electronegative atom, an oxygen from a different water molecule. So the hydrogen bond here would look like this. I'm going to choose to draw dashed lines here to indicate that. So what I've just drawn, that is the hydrogen bond, or the H bond, okay? Now, notice that one of the water molecules is involved using its lone pair, and the other water molecule is involved using the hydrogen. So we actually give these two molecules names, or the groups that they're involved in the hydrogen bond, different names. So the water on the top, and particularly the oxygen here, this is called the donor, right? The hydrogen bond donor, because it is kind of letting the other water molecule borrow this hydrogen, okay? And then conversely, the other oxygen on the other molecule over here, this is called the acceptor, because it's accepting the hydrogen from the other water molecule. Now, to be clear, these names are bad, because if I donate something, I don't expect it back, but that's not what happens here. This water molecule on the top, we call it the donor because it's providing the hydrogen for the hydrogen bond, but it keeps it. This bond, as a covalent bond, stays put. It does not go away. So although we use the term regularly, donor and acceptor, hydrogen bond donor, hydrogen bond acceptor, I'm going to put them in quotes because really they're bad names, because if I donate something, I shouldn't expect it back. But that's just the way the nomenclature, unfortunately, has worked out. So just be familiar with the proper definition of a hydrogen bond, and then also what the donors, acceptors, and what the hydrogen bond itself is, and that we're going to use dashes or dots, not solid lines, to show that hydrogen bond. Okay, so that's water with water. Let's also show water with something else, like methanol. So I'll go ahead and draw that out. Methanol we can draw like this. So I'm going to draw out the bonds a little more clearly than we showed before. And I'm going to show two different water molecules interacting with it. In one case, I'm going to have a water molecule kind of over here to the right. And it's going to interact with the hydrogen from the methanol. And so again, just to be clear on this, right, because this oxygen is pulling electron density away from the hydrogen, this is a partial positive, and then the oxygen again on water is a partial negative. So they can have a hydrogen bond like this. Again, this meets the definition of a hydrogen bond because we've got a hydrogen covalently attached to an electronegative atom, and it's also interacting with the lone pair of another electronegative atom. So in this case, because this water molecule is accepting the hydrogen bond, this is then the acceptor. This water is acting as a hydrogen bond acceptor. But methanol has, again, that oxygen, and the oxygen can also engage in a separate hydrogen bond with a separate water molecule. So I could draw another water molecule down here. Notice I've oriented it differently. Again, the oxygen carries the partial negative charge, and now this hydrogen on water carries a partial positive charge, and I can show the hydrogen bond as a dash there. And now this water molecule is acting as the donor because it's providing the hydrogen for that. So here we can see methanol can engage, and water can both engage in being donors and acceptors. What cannot happen is these hydrogens here that are attached to the carbon, these cannot be involved in hydrogen bonding because they're not polar. So just make a note of that, right? Those are CH bonds. Cannot H bond because they are non-polar. We really have to have our hydrogen bonded to an oxygen or a nitrogen, maybe a fluorine if we come across that. So be able to draw these types of interactions and label them and understand what's going on there. All right, another one I want to talk about is the ion-dipole interaction. This is a pretty strong interaction where we have essentially a charge and a partial charge, if you want to think of it that way. So we've got a charge and partial charge. Kind of another way of saying ion-dipole. So for example, let's look at a metal ion with a carbon-oxygen double bond. So I'm going to abbreviate metal as just capital M plus 2. So it has a charge to it. Could be calcium or magnesium, whatever. We're not really specifying that. And that can interact then with an oxygen that's, say, double bonded to carbon. This could be acetone. It could be some other larger thing. We're not too worried about what's attached to it. We're kind of focusing in on this part here. So typically, as we've seen, right, that oxygen is going to carry a partial negative charge, and very clearly the metal already has a formal positive charge too in this case, but this is going to have an interaction like that, and that can be a really strong interaction because of that charge really drawing those electrons in the lone pair of oxygen to the metal. Now, or we could have other charge dipole interactions. I'm not going to show a ton of them, but it could be other things that maybe it's not a metal, maybe it's an organic molecule or part of a protein or something like that. So we'll see examples of that as we go along. But if you see a formal charge, a plus or a minus, interacting with a partial plus or partial minus, then that's going to be a charge or an ion dipole interaction. And then finally, there is another type of interaction called London forces, or this is where we get instantaneous dipoles. And you will often see this referred to as nonpolar interactions. So what happens here? Again, I'm going to show electrons sort of as little dots here. And we're going to think about, say, molecules A and B that are connected, or I should say atoms A and B that are connected into a molecule. And we're going to say that this is nonpolar, right? So the electronegativity of A and B is about equal. So this could be a carbon-carbon bond or a carbon-hydrogen bond, whatever. And they have, therefore, roughly the similar electron density around them. So about 12 electrons or so around each one. Doesn't be exactly right, but something like that. So similar electronegativities, but what can happen is random, just because of statistics and quantum mechanics and all these sorts of things that we're not going to talk about, just by pure coincidence, by happenstance, because electrons are zipping around, it's possible that suddenly the molecule has an imbalance of electrons, that just by random statistics, there's more electrons around A. So the electron density kind of shifts that way a little bit. And so we could show that as something like this, where A, so again, bonded to B, but just in this one instant in time, A just happens, just by pure coincidence, to have more electron density around it. And that then means that it's going to have a partial negative because it has more electrons, and B is going to have a partial positive. So it's like this random instantaneous dipole that just happened to occur. Now it's going to go away really quickly, but before it goes away, what it can do is it can interact with a nearby molecule as well. So let's say there's another A-B pair over here. And just because this has this positive charge, or this partial positive charge, it's going to induce a dipole in this neighbor molecule. So now this partial positive is going to kind of pull electrons toward this itself, or towards the partial positive charge, and we'll end up with a similar situation where now we have more electrons on A and slightly fewer around B. So now we got a partial negative here and a partial positive here. And that can kind of keep on happening. I'll say et cetera. It can keep inducing, this instantaneous induced dipole can keep inducing other dipoles. Now they go away really quickly. And they're coming and going constantly. So they're pretty weak as a result. London forces or nonpolar forces are pretty weak, this interaction is. However, it's present in all matter. All matter has this polarizability to it, and so it becomes important. It especially becomes important when molecules are bigger, because the bigger they are, the more polarizable they are, the more impact the London forces will have. So we're going to say the statement here. The larger the molecule, the stronger the London forces are. So a small molecule, A and B are the only atoms in it. The contribution of IMFs from London forces is going to be small. If A and B repeats itself over and over again, it's a bunch, it's much bigger. You got AB, 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 or something like that. Then there's going to be a larger molecule. The London forces will be stronger. So now that we understand those things, let's look at the relative strengths of these forces. And so we're going to rank order these weakest to strongest. And so the weakest one are those London forces, or those nonpolar forces. And next up from there are the dipole-dipole interactions. And then remember, hydrogen bonds are a type of dipole, but they're so special that we're going to kind of give them their own category. Hydrogen bonds are the strongest dipole-dipole interactions typically. And then ion dipole, most of the time, are the strongest of all of these. And then none of these are as strong as a covalent bond. The covalent bond, being an intramolecular force, is actually stronger than any of these. But point being, London forces are super weak, and then hydrogen bonds are pretty darn strong. And then dipole-dipole interactions are kind of in the middle. So we're going to pay a lot of attention to those. So if we understand these intermolecular forces, we can go on and think about things like melting points and boiling points and how the structures of these molecules affects their properties. So what we're going to do is look at three molecules, methane, methanol, and ethane, and you might not know what those are based just on their names, but we'll get there in this course eventually. So methane is a formula CH4. Its Lewis structure looks like this, where I've got a central carbon, and then I've got really just 4 hydrogens around it. That's its Lewis structure. So that's methane right there. Now, what IMFs can this have? Well, every matter, all matter, has London forces. I'll choose a different color just so it stands out. All matter has London forces, so we can always write that down. But notice that this has CH and bonds only. Those are nonpolar, so there are no dipoles, there's no hydrogen bonding, there's no ion dipole. This is the only thing this molecule can do, is this London type interactions. So we're going to say London forces only. Okay, next up is methanol. So I'll draw that over here. Methanol, I'm going to simplify it a little bit. We'll do CH3, and I'm going to draw the OH like this. That's methanol. So what IMFs can it have? Well, it can have London forces, because all matter does. And notice it can do a couple things. First of all, it's polar for sure, because it has, say, a CO bond, so those electrons are being pulled towards that oxygen, so this is a polar bond. It has an OH bond, also a polar bond. So we can add to this dipole interactions. But very specially, it has the ability to hydrogen bond, because, let me just add the lone pairs quickly here. Right, this methanol, like we just saw on the previous page, can act as a hydrogen bond donor with this hydrogen because it's covalently bonded to this oxygen and can interact with a lone pair, and it can accept a hydrogen bond from another molecule. So methanol can engage in hydrogen bonding. And then finally, the last one here, ethane. Ethane has the Lewis structure like this. It's 2 carbons bonded to each other, and then hydrogens pretty much everywhere else to fill up the octets of those carbons. So that's ethane. And just like it was with methane, notice that it's all CH, CC bond in this case. So this is a nonpolar molecule, and it only has London forces, aka nonpolar interactions or nonpolar forces. So the thing about boiling point, melting point, right, it's how those molecules cling together. So molecules with stronger IMFs will have higher melting and boiling points. You can think about those molecules kind of clinging together, and it takes more and more energy to pull them apart if their IMFs are stronger. So we want to rank these by increasing boiling point. And it's a question, which one's going to be the lowest? Well, think about this, right? I just told you hydrogen bonding is a really strong intermolecular force. So methanol is going to win the race here. It's going to have the highest melting point or boiling point because these other two can only do London forces, and those are the weakest. So methanol is definitely the highest here. Then the question is, well, which comes first? Which is going to have the lower melting or boiling point? Is it going to be methane or ethane? And this goes back to the previous page where it has to do with the size of the molecule. The larger the molecule, the stronger the London forces are. So with methane being a smaller molecule, it has a lower melting or boiling point than ethane does because ethane's a bigger molecule. So that means that methane is the lowest. Again, we're going by increasing melting point. And then methanol is going to be the highest. Next up, though, is ethane because it's a little bit bigger, but it still can't do any dipole interactions or anything like that. And then methanol, because it can hydrogen bond, has the highest boiling point or melting point. And those track with each other, so you can kind of use them interchangeably, melting versus boiling. All right, let's talk about solubility in water. In general, molecules that are charged or polar are going to easily dissolve in water because water has that strong dipole, and so it's good at dissipating or interacting with charges. So let's say, for example, I had a sodium ion, Na+. It could interact with water molecules because water has those lone pairs, and I'm just kind of drawing an arbitrary number of water molecules around it, and actually depends on the particular ion how it's going to interact, but we're not going to worry ourselves too much about that. But notice that I've chosen to draw these water molecules such that their partial negative charges are interacting or facing the sodium. And so kind of the flip side of that one would be a negatively charged ion, a chloride anion, for example. And similarly, water can interact with that because it has a dipole, but it's going to flip that around and it's going to interact via its partial positive side where the hydrogens are. And again, you can draw some arbitrary number of those on here just to kind of get the idea. And then we've got things like dipole and hydrogen bonding. So those are those polar molecules that can do those things are going to have a very good solubility as well. So for example, we looked at acetone, so you could think about something like that, right? If I'm a water molecule, I actually have the ability to hydrogen bond with acetone. So I'll draw a hydrogen bond in like this, right? It's also, polar, so you could have polar interactions, dipole interactions as well, because of the partial charges. So things like that. Also, so that's like acetone, something like, as we'll see later on, an alcohol, like the methanol we talked about, that again can interact with water quite readily, as we saw. So I can draw water like this as well. Right, so things that are polar, and especially things that can hydrogen bond, those are going to be soluble in water. However, things that are not going to be soluble in water are non-polar substances. They do not easily dissolve in water, and they will form separate layers. So think about when you mix oil plus water, or Italian salad dressing. I think we kind of have this feeling, these things aren't going to mix, or you can shake them up, and maybe they kind of mix for a little bit, but then they settle back down and become separate layers. Well, it's because these things can't form hydrogen bonds. And or have any polar groups at all to form any polar dipole-dipole interactions. So the key thing here is that something like oil, right, cannot form hydrogen bonds or dipole interactions, INT. And the reason they're nonpolar, right, is because we're talking about things that have lots of CC or CH bonds, and those just aren't very polar at all. And so that's why these aren't going to be able to engage in those interactions like we showed up here with the polar substances or the charged substances. And so one thing I want to point out is that the larger the nonpolar molecule is, the less soluble it is. And again, we're talking about in water here. So something with a lot of nonpolar surface area, lots of CC and CH bonds, is going to be far less soluble in water than maybe just a smaller molecule. So we call this the hydrophobic effect. The fact that these are going to tend to form separate layers, again, like oil and water. And we'll talk much more about what the hydrophobic effect really means, because it's pretty key and pretty important when we're talking about how proteins fold and how your membranes are made. So we'll get into that one later on. But for now, let's think about solubility and how, the three molecules we've been talking about, how they will be soluble, and we'll rank them again, increasing solubility. So think about the types of interactions that can go on, right? I'll point out that methanol, as shown above, can hydrogen bond, and it can has a dipole, so it's definitely polar. So methanol is going to be very soluble in water, for sure. Methane and ethane, on the other hand, right, these are molecules that have no dipoles at all, cannot hydrogen bond, cannot engage in dipole-dipole interactions, so these are not going to be soluble. And then the question is, which is worse, methane or ethane? Well, here's the thing. Like we said, the bigger the molecule, the less soluble it is, right? So something like ethane is actually going to be the worst here because it's a bigger molecule, more nonpolar surface area, and so it is the least soluble. Methane's a little bit smaller, so it can dissolve a little bit more readily into water, but not very well. And certainly because methanol can hydrogen bond and engage in dipole-dipole interactions, it's the most soluble. So that is the correct order for solubility for those compounds.